So now when we talk about the periodic table, we're going to talk a little more in depth about the periodic law. In other words, why the periodic table is arranged the way it is. So you already know that there is a big change in terms of metallic character as we go from left to right. So now we're going to expand on what metallic character means in terms of the other properties. And specifically, the properties we're going to focus on are atom size, atomic radius, ionization energy, electronegativity, valence electrons, and size of ions. Now, electronegativity we're going to just briefly hit on because the next unit we spend a lot of time discussing it. Now, let's back up. Periodic law is the idea that properties are a direct result of the atomic number. That means there's something going on between the actions of the electrons and the protons. We know that electrons and protons experience an attraction, what's known as an electrostatic attraction. Opposites attract, likes repel. And ultimately, when we look at the trends are a result of those interactions between protons and electrons. So one more time, opposites attract, likes repel. So ultimately, all of our trends here have to do with these two interactions. So the first thing we're going to deal with is what's known as atomic radius. Ultimately, how large is the atom? So simply the size of the atom. Okay. Now, how they measure this is not as important to me that you know. What I want you to know is simply what's going on with the size of the atom and why the size of the atom changes. So if you look at this 3D chart, they've created this model to demonstrate how the atom size is changing. So typically speaking, we see it decreasing from left to right. So that means lithium is bigger than beryllium, which is bigger than boron, until we get all the way here to fluorine. And so we see a decreasing atomic size from left to right across the row. Okay, this is due to the increasing nuclear charge. In other words, the number of protons. So as you go across, we know the number of protons increases. Well, let's go back. What did we say were ultimately responsible? The opposites attract. So if I have a lot more protons and a lot more electrons, I have more attraction, and literally the atom gets made smaller. Now, from top to bottom has to do with the increasing number in front of our electron configuration. So lithium and sodium are in the first column of the periodic table, the alkali metals. Lithium's on the second row, sodium's on the third row. That number there, that 1, 2, and 3, that's what we're referring to when we say the increasing value of. In other words, we add a shell of electrons. And so as we add electrons, the orbitals and the shells, we push the electrons further and further away from the nucleus, and the size of the atom increases. And the atom size actually has an increase on our ionization energy. Now remember from the previous section that ionization energy was defined as the energy to remove electrons. What we get to see here is every time we remove an electron, it requires energy. So not all of our elements lose only one electron, some lose more than one electron. And so what you're seeing with this chart is you're seeing how much more energy is required to move each successive electron. And again, it makes sense. If I lose an electron, that means the existing electrons are going to shrink in size. They're going to get closer because there's fewer electron repulsions. If there's less electrons around pushing each other away, you can occupy a smaller and smaller space. And I still have the same number of protons because the proton number doesn't change. So what we see is we see a very predictable pattern. We hit what's known as that wall, and that's what's recognized. That's what they're showing you here with the blue. So you go from 495 kilojoules to 4,562 kilojoules. So sodium's only likely to lose one electron. Magnesium is 738, 1451, and then 7,000. So again, magnesium is only likely to lose 2 electrons, and that's all they're talking about. So when we take away this first one, that's what's known as first ionization energy. First ionization energy. I moved things around, dang it. First ionization energy. The second one here will be my second ionization energy, and so on. So each successive one, notice that we increase with each electron we have to remove, and that's ultimately the point. So in general, since it's impacted by the atomic size, since we know my size of an atom decreases from left to right, sure enough, the ionization energy increases. So atom size decreases, ionization energy increases, and that makes sense. The electrons are closer to the nucleus. It's going to take more energy to take them away. So ultimately, it's the distance from the nucleus that determines my ionization energy. Now, when you graph this, which you guys actually will be doing, you can see that it generally increases from hydrogen to helium, lithium to neon, sodium to argon, potassium to krypton. We see that increase in ionization energy. Now, there are a few exceptions. We don't need to worry about the exceptions. I simply want you to know about the first versus second ionization energies. So the next thing is simply the size of the ions. Now, it makes sense when you think about it. Remember that there are two properties of matter. We know that matter has mass, we know that matter takes up space. So those two properties tie nicely into the parts of our atom. The nucleus is what's responsible for our mass. That's where we get our mass number. When we look at isotopes, remember the average atomic mass, that's all from our nucleus. When we talk about space, we're talking about volume, we're talking about electrons. So when I change the number of electrons and the orbitals those electrons occupy, I literally change the size of the ion. So cations, by definition, are positive ions. They've lost electrons. If they've lost electrons, you literally see them change in size. They get smaller because there's fewer electron repulsions, there's less electrons in the space, they can get closer to the nucleus. Conversely, anions are our negative ions, so they've gained electrons, and that gain in electrons increases electron repulsions, increases the occupied space, and so we literally see all of our negative ions larger. Notice that it's larger than the original ion. So potassium is a rather large atom, but because it loses electrons, it's smaller, but it's still larger than sodium and lithium ions. So the trend of size still mirrors what we see with atomic size. Ion size is going to increase as you go down the column because we have an increasing number of orbitals. We see a general decrease in cations, and then we see a subsequent increase in the anions. And that's again due to the increasing or the changing number of electrons. Now, more detail on valence electrons. Basically, how do we recognize valence electrons? How do we help to recognize that when it was mentioned the core electrons that were associated with the electron configuration? And that's what we represent with our noble gas part when we do the shorthand electron configuration. That represents what's known as the core electrons, because remember, we may know where the final electron is, and we know that everything below that is filled. And that's ultimately the point. So when we look at elements like this, the valence is the highest number, so the 5 in this case is the highest number. So this element has 4 valence electrons because there's 2 in S and there's 2 in P, so that's 4 total in the 5th orbital. So we have 4 valence electrons. This is the same, or we see the same number of valence electrons in every column of the periodic table. If I have S1, then I have 1 valence electron. S2, 2 valence electrons. Well, as soon as I hit P1, remember everything below is full, so I have 1, 2, 3 by the time I get here, and I have 3 valence electrons. The cool thing about this is how it's reflected in the periodic table. Remember S1, S2? Well, notice I have 2 different number systems going on. I have the A's, and then I have just the numbers. So I have a 1A, a 2A, 3A, 4A, 5A, and then all of these B's. So remember, these are the D block metals. They are what are known as the B block. In other words, they're not representative. The representative atoms is always referring to the A's, to the S and the P block. So when you look at the trends, you will notice that all of the images of the periodic tables were actually just the S and the P block. We kind of ignored the D block because, again, remember from the previous unit, the previous section of notes, the D block atoms are almost all the same size. So we don't see a lot of change. We don't see the trend that we see with the S and the P block. And notice again, first column, 1A, 1 valence electron. Second column, 2 valence electrons. Third column, 3 valence electrons. So we see the pattern of valence electrons playing out in the numbering of the columns. Now, here's another little thing that we'll be working on in the next unit with greater detail, and that's where we list that valence electrons, the number of valence electrons, as dots around each atom. And you may have seen this before in previous classes. These are the electrons available for bonding. In other words, these are the electrons that are gained or lost to form positive or negative ions. And the last property we're going to talk about is electronegativity. Electronegativity is simply the likelihood of an atom to attract electrons. Is it going to take electrons when it's in a compound? Nonmetals have higher electronegativities than metals. And again, this is reflected in the ionization energy and the atomic radius. So we see how all of these trends are linked together. So, brings us to our questions. Pause the video, answer the question. This is just a nice general question. Why are periodic trends important? Ultimately, because it allows us to figure out how, gives us an idea of the properties and how they're going to react. So if I know where an element is in the periodic table, I can predict its chemical behavior. So here's the next one. Pause the video, answer the question. So you should have gone and found it on the periodic table. Notice that francium is, oh wow, all the way on the bottom left of the periodic table. So that means that it's going to have a very large atomic size. And if the atom size is large, then that means the ionization energy is small and the electronegativity is small. So the answer here is 4. Last question, make sure you pause the video. So the thing here was the largest radius. Remember what we just talked about with ions? So I would have been looking at where all of these were on the periodic table, and then I would have actually probably started here because I know a negative ion has a larger radius than the parent atom. So then I'd look where is the parent atom and look at each of these, and lo and behold, this one's going to have a larger radius than this one. It's to the left. It gains 2 electrons, not just 1. And this one lost an atom, so I know to eliminate it immediately.